or am I going to be recording this? All right, that speaks for itself. Anyways, so this is the iterators and generators topical review session. These slides, I put the link in the chat, but links.cs69.org/timslides. These are currently just my discussion slides, and they're under discussion 8. So we'll just be going through some of the topics before going into like practice questions and maybe even switching into a different batch of slides. Okay, so iterators and generators. So we'll talk about this concept briefly. So for iterators and generators, there's something called the idea of lazy evaluation, which means that certain things are not like evaluated or like calculated until you do some particular function call. So for iterators and generators, that's a call to next. However, if you remember like from Scheme, let's say, this is the idea of like streams. Anyways, there are a few benefits to lazy evaluation, notably that you can define infinite structures, because if you had a truly infinite structure and tried to represent as a real data structure, that would take an infinite amount of space, which is unreasonable. So instead, we can use lazy evaluation to do practically infinite structures, which are things that are not truly infinite, but they can be treated as infinite, assuming we're to say call like some function again and again and again. Anyways, so for a brief analogy on iterators and iterables, we tend to use like this bookmark analogy. So here we've got like this picture of a book with some bookmarks. And so we can think of an iterable as a book. And a classic example of an iterable is a list. And so an iterable would be like, let's say, a list of different pages you're on. And we could then think of iterators as bookmarks. So if I were to say, have some iterator or some bookmark in the book, it would track some page, and I can move this iterator or this bookmark around the book and to track which particular page I was on. And for the iterators referring to, our only operation currently is to just flip the next page and put the bookmark in that next page. So like while we're reading, we flip the next page, put the bookmark in, and then maybe we leave it there. And if we want to come back later, we can flip to that particular bookmark and then start reading from that point and getting information from that point. What's another important note is that an iterable or book can have multiple different iterators or bookmarks. So see in this particular example, we've got many different bookmarks, all keeping track of different pages or elements within some iterable. So here's just a brief summary here of what I said. So let's talk about some like terminology. So iterables are some data type which has some like collections of values. And what's important is that they have to have some sequence, so some sequential order. So lists, dictionaries, tuples, and strings all fit this idea of an iterable because you can process them individually, and they're all just collections of return values. So like strings, are collections of these different characters. You can go through them one by one. Or more broadly speaking, anything you can loop through. So if you can do like for I in blank, you are looping over some iterable object. An iterator with this bookmark is an object that retrieves values within an iterable or like keeps track of values within an iterable. So here are some of like the main functions we use when we're dealing with iterators and iterables. So the first one is iter of iterable. So what this does is that if you have some iterable object, say a list or a dictionary, you can call iter on that list, say iter of list, and it'll return to you an iterator. And you can think of it as you've got a book, and you put a bookmark at the very first page. A notable exception of this is you can also call iter of an iterator, because iterators are also considered iterables. So now this like diverges a little bit from this bookmark analogy, because it's a little bit weird thinking about putting a bookmark into a bookmark. But here, when you call iter on some iterable or an iterator itself, you get the exact same iterator back. No changes at all. It's the very same object. Another operation we have, or another function we have, is calling next on some iterator. So if we think about the bookmark analogy again, we have the bookmark. When you call next, we'll get the page where that bookmark is, and then we'll flip the page and put the bookmark on the next page. So here it gets the value within that iterable, and then we'll shift the iterator's position over. So for an example of how this would look somewhat visually, we would have a list containing 1, 2, 3. This is our iterable. And then you can create an iterator called A. So here we've got an iterator called A at the very start of the list. And we call next on A. So calling next on A would give us the very next element here. So 1, wherever the iterator is positioned. And then it position the iterator at the next spot in the iterable. So now it's on 2. Call next on A again. It'll give us the element here and also shift the position of the iterator. And B is equal to the iter of list. What this means is that we're just going to go ahead and create another iterator for this same iterable object. So put another bookmark in. So put another iterator here. Call next on B again. It still gets us 1. Next on A will give us 3. We're just keeping track of A now, not B. And now an important thing to note is that if you were to call next on A and there are no more elements, you would get what's called a stop iteration error or exception. Because there are no more elements, we can no longer try calling next on this list. So here, fun fact, yeah, iterators are iterables. So you can call like a for loop on some iterator object. And so here, if you want to look at a particular diagram here, iterators are just like a subtype within iterables. So that's why, iterators are within iterables. And we could do the same exact behavior as if iterating through the list itself. So if we create A is equal to the iter of this list, we can still do like a for loop here. So for element A, print element, we will still get 1, 2, 3, and that'll still work fine. And we could have also, done for element in iter of A, because iter will give us that same iterator. All right, so now we're going to do some like WWPD. I'm trying to remember if this was directly the same as the discussion. It might be. I'll try doing some brief things from chat maybe, if you want to give an answer. So let's say we have list of 61A, and what will happen if I try to call next on this list? So what will the terminal output? Oops, error. Okay, there aren't too many people here, so I think it's a little bit redundant doing a poll, or a little bit excessive doing a poll. So yeah, it is actually an error here because the lists themselves are not iterators. So we can't call next on it. That's just not a function that applies to iterables. Rather, it's for iterators. So now instead, if we make an iterator out of this iterable object called list iter, we can call next list iter, and it will give us 6. If you call next on list iter again, sure, I'll take some more answers from chat if you want to give some answers here for what the next value would be calling next to list iter. Does anyone else want to give an answer? If not, that's okay. It will be 1 because if we think back to our original analogy, we sort of list iter is still in the same spot as before. You got the 6, and then I'll go ahead and annotate real quickly here actually. So you were at 6, but then you moved on. So now you're at 1. And then we can do next of iter of list. And so what will that give us here? 6. Do you have any other answers? Yep, it's going to be 6. So let me put these things in the correct position actually. So currently, I've got the A on here. And what we've done here is we've created a new iterator from this list that's positioned at the very front. And then you call next on it. So we create this new iterator, and then we call next on it. So we're going to shift it over. And in the process of doing so, we got the element that was being pointed at by this iterator. So it's going to be 6. So what about x for x in list iter? What are we going to get here? A with a question mark. But yes, it is going to be A here because list iter still refers to this red arrow here, and it's pointing at A, and the only elements that are left within this iterable is just A. So we get A. And now, let's say we do list iter of 2 is equal to iter of list iter. What's going to happen now? I think, yeah, and then we call next on list iter of 2. So what's going to happen there? Stop iteration. Do you have any other ideas here? So also for, I'll finish it again. Oops, this is supposed to be here. Stop iteration. But yeah, it is going to be stop iteration here. So recall before that when you do x for x in list iter, that's the same thing as iterating over every element within this list iter, which is just as A. And then now it's, it's moved on. It's the very end. It's going to stop iteration. And when we call iter on list iter is still here. So we return this very same iterator. And so next of list iter 2 will just be stop iteration. Okay, let me go ahead and annotate clear tracks. So generators now. So generators are like iterators, except we've defined them using some particular functions within Python and with some particular syntax. So here on this diagram to the right, you'll see that this chart showing the relationship between iterables, iterators, and generators. So generators are just a subtype of iterators, iterators just a subtype of iterables. So generators are some iterators defined using functions, and generator functions will return a generator object or an iterator. And we can define these generator functions by using these yield statements and or alternatively yield from statements. Okay, so for the particular behavior of yield, how it works is that you will run the code until you get to a yield statement, and then you will yield the value at that point. And every time you call next on this generator object, you're going to continue running the code. So you can think of it as being the code is frozen at some point. And we call next again, it unfreezes, and you continue until you get to the next yield statement. And like so on and so forth until you eventually, run out of code to run. So here for this particular example, you've got this function called countdown. So in the beginning, this is a generator function. So it's going to yield a generator object here. So if you call countdown of 5, it'll return us a generator object. So A is this generator object. And then we can call next of A. So here, we said, let's say, within countdown, we initialized 5 to 5 here. And then we're not going to be running any code. Instead, we're going to start running code when you call next of A. So next of A, we see, okay, 5 is greater than 0. Then we yield 5, and then we stop. We don't continue until later on. And then we get to call next of A again. So we go back to this yield statement, and we see, okay, and it's 5 still. We're going to subtract 1 from 5, get 4. Go back to the top of this while statement. 4 is still greater than 0, and then we yield 4. And then now we're done. Or now we're going to stop for now and freeze, essentially. So now for yield from is another thing called syntactic sugar. So essentially it just means that it's like a more clean way of writing something that could be written in a longer form. So here, if we have something like def yield list of list, we can do like something of 4 elements in list, we're going to yield the element. So we're just yielding all the elements from this particular list. And if we want to put that in a slightly shorter form, we could just yield from the list. And these two are equivalent entirely. Okay. So now we're not going to be doing that. Instead, we're going to be switching over briefly to these slides to talk about some more things here. So most of these ideas within these slides are pretty much the same as what I had before. Iterables, iterators. There's one notable exception. We will be talking about try and exceptions. So if you try to do some, let's see. Okay, Akshat, right, Akshat I think wants to talk at this point. Would you like to go ahead, Akshat?
Yeah, I can take over. So I'm going to share my screen using an iPad. Tim pretty much covered everything about iterators and generators. So what we're going to do now is mainly just some problems and try to apply some of the stuff he said. The first thing I want to briefly mention is this. Once again, the distinction between generator objects and generator functions. And we'll see that very nicely in this question. So take a second and read this, and then someone tell me in the chat what the output would be. Error, okay. Yeah, so it is going to error. And the reason, oh wait, sorry. Yeah, so the reason it's going to error is because when you call next, this 1 divided by 0 happens. But I guess the important thing I wanted to point out is that when you say x is equal to generator of 5, then you say x is equal to a generator object. But none of this function body actually got executed. So typically, if this was not a generator function and like you had just crossed out this yield line, just this first line would error. But now, like this, calling this generator function is giving us an object that we can then iterate over. And using the same analogy of like the book and the bookmark is just placed here in our object. And next time you call next, it'll go and it'll execute this next line. So yeah, that's just a 0 division error. But let's go ahead and start doing some problems now. And these are in the slides that are posted, by the way. So here's the first problem. It's a generator function that takes in some iterable and is going to return an iterator over all of the unique elements of its input. So what that means is, for example, it would take in like 1, 3, 2, 2, 5, 3, 4, 1. And it would give back 1, then 3, then 2, but then it wouldn't give back the 2 twice. So notice we have 1, 3, 2, but we don't have another 2. Then 5, and there's no 3 because we've already yielded a 3, and then a 4. And this is a generator function, but you have some restrictions here. You can't use def for or any class statements or any lambda expressions. So yeah, you're a bit limited. So let's take a few minutes to give this a shot, and then hopefully we can talk about it. If you aren't sure like what isn't forbidden here, a while loop is not forbidden. So you should try to use a while loop. So let's start to talk about it. If someone is willing, can you unmute your mic and maybe share like how you approach this problem? Chat is fine too.
I can explain.
Go ahead.
I'm not sure if this is right, but my thought process was that I would want to first use the while loop to edit the iterable. So that way the iterable would only contain unique elements.
Okay.
And then after I'm done editing it, I would just return iter called on that new iterable. So the way I did it was I basically initiated a new list to be an empty list. And then had a while loop where while the length of the iterable was greater than or equal to 1, I checked with an if, so if iterable at index 0 is not in list, I appended iterable at 0 to new list, or I guess list in your case. And then I made iterable equivalent to iterable sliced at 1 onwards.
Okay. Yeah, that makes sense. One assumption that I think, never mind. I guess the only assumption we're making here is that iterable is finite and it's something that has a length, which we don't necessarily know. Or I guess my main point is that we're sort of like constructing the iterable that we want to yield from before we actually need to, which goes against the spirit of like only compute stuff like as you want to. But this totally makes sense. I think we could do this and then, as you said, return an iter on the list that we constructed. The way we approached it was actually using generators and like this concept of lazy evaluation where we only yielded something like when we needed to. So I'm going to write it on the right side. And the way we did it was somewhat similar to what you did, except instead of like constructing a list that contained all of the elements, we kept a list of all of the elements that we've seen so far. And if we have that sort of list, then we can just iterate through like our iterable, and then if like we see something in our iterable that isn't in our like seen so far list, then we yield it. And the way that might look is initialize some list like observed to be empty, so you haven't observed anything in the beginning, and then have a while loop that goes through and iterates through the iterable. So I guess we also decided to use iterators here to actually like get elements one by one from the iterable. You kind of got around that by using slicing. I believe you should be able to use slicing still. But what we did was we constructed an iterable from the, or iterator from the iterable, and then repeatedly called next on that. So we can say like val is equal to next of that iterator. And then if that val was not in observed, then we can yield that val and add it to observed. Does this make sense as well? Okay. There is one problem with this, and that will actually occur if our input iterable is finite. Does anyone know what it might be?
Will it not add that last value to the list?
The last value.
Because we stop after the yield, right? So if it's finite, then the last one won't be added.
If the last one, so the last one might not be added to the observed list, but we don't really, or actually it would be because we'd run through this function. Or the way it would work is like, for example, like if we had some input iterable like 1, 2, 3, then we'd say val is equal to next of our iterator. So val would be 1. We'd yield val, and then we'd do this line. Then in the next iteration of the loop, we'd yield 2. And then in the iteration after, we'd yield 3. But then we'd, like, if we call next on this iterable again, like it would do this observe.append val. But really, we don't really care about what goes in observed as long as we yield the right stuff. But there is some sort of error that will occur if we repeatedly call next on an iterable, like when it runs out of elements. You might have seen earlier, if you call next, but there's no more elements in the iterable, then you'll get a stop iteration error. And that's what we have to deal with here as well. And this is what Tim was mentioning a bit earlier. In order to deal with stop iteration errors, we can put our code in a try-catch. So basically, I can take this segment, indent it a little bit to the right, and say, try doing this. And if not, so if there's some sort of error, which is a stop iteration error, then just exit out of this loop. So we could do something like return, or we could do something like break, whatever terminates our function. And the reason we made you like try this like without using a for loop is because what we're doing here is actually like exactly what a for loop does. What a for loop will do is it'll take some iterable, it'll call iter on it, it'll in every iteration, it'll call next to get a value, and then this segment is like what you would put in the for loop, and a for loop will handle the stop iteration error for you. So you never need to see like that this stop iteration stuff occurs. So the equivalent code of this would be something like observed is equal to an empty list, and for val in iterable, you if val was not observed, yield val. So once again, this for loop is like syntactical sugar for a while loop that does all this special handling. But yeah, hopefully that gives you a bit more insight into how the for loop works. Do we have to specify what type of error to expect? Or the way I have it now catch any error? The way I have it now does catch any error, but we can specify if we want to only catch a specific type of error. So I believe we can do something like except stop iteration error. We can take a look at the solution here as well real quick. They flip the order between these, but that shouldn't really matter. Are there any questions about this? Great. Yeah, we can try to do another question. I think one more thing. I don't believe that you can index into any iterable. So I'm going to take back what I was saying earlier. I can verify this real quick. But actually, yeah, let me just verify it real quick. Yeah. So I think you have to override some special properties in order to be able to index into things. And lists do that, strings do that, and tuples do that. But a generic like generator object might not.
I could the exception to think about is if you just pass in some iterator into this unique, like, so you called iter on this list and you pass it in, and you can't call len on the iterator since like your bookmark technically doesn't have a length.
Yep.
for
We
more
can't
specific
pass in an
reasons.
iterator, exactly. So if our input was like just iter of that, then this wouldn't work. But yeah, this has the same exact idea as what we did. Cool. Let's try another question. This is even more explicitly a generator question. And the idea is that we're implementing some generator. It's called PowNaturals, which yields a bunch of generator objects. So we have a generator that's yielding generator objects. And each of these generator objects is going to yield sequential powers of a natural number. So the first generator object that we yield is going to yield the powers of 1. Then the next generator object is going to yield the powers of 2, and so on. And you can glance at the doc test here, where the next of this generator, so the first element, is a generator P1 that yields all the powers of 1. And then P2 and P3. So take a few minutes to do this again, maybe 3 or 4 minutes, and we can talk about it after.
Yeah, and if you have any questions, just feel free to ask or PM one of us. Either that's fine.
Hey Google, set alarm at 6.
let's start talking about it. So yeah, does anyone have any ideas on how we can start?
Just for, I guess, some peace of mind, how many people were able to get through the problem? So, okay, I'll rephrase it actually. How many people are not done with the problem? So if you're not done with the problem, just put in chat that you're not done. Here, one person is lost. Is anyone else done or lost, or where are people at? Okay, yeah, it seems like people are having some difficulties with that.
So I guess we can start off by giving a bit of hints. So we know that our overall function has to yield a bunch of generator objects. And we have this like helper function that's conveniently defined for us. And we can actually use this to get back generator objects. It takes in two parameters, n and p. So maybe it'll yield n to the power of p. And then yield from n to the power of p plus 1 and n to the power of p plus 2, and so on. So try to define this generator want to actually link the generator objects. Now, how do we get the generator objects? We just call the helper function that we define, and that'll give us back a generator objects. What generator objects do we want? Well, the first generator object that we want is one that yields all the powers of 1. So maybe something like pow of 1 comma 1, because that will yield 1 to the 1, then 1 squared, and then 1 cubed, and so on. But more generically, we might want like the powers of n, because first we want 1 to the power of 1, but then the next time we can increment n and then get the powers of 2, and then get the powers of 3, and so on. So try to take a couple more minutes and give this a shot, and then we'll talk about it.
Yeah, for now, if you do get done, just go ahead and like say so in the chat, like, or if you are still confused, you can also put that down in the chat, just so we have an idea of where people are, because we do have some more questions to go through.
It's fine if you message us privately also.
Yeah. All right. Since I think we have other content to get through, I think we're just gonna go through the solution. Yeah, do you want to go ahead, Akshay?
Sure, let's do that. So let's try to use the two hints that I was talking about earlier. Pow can be a generator function that yields all the powers of n, starting with the pth power of n. So for example, if I do pow of 2 comma 1, that should yield 2 to the power of 1, and then yield 2 to the power of 2, then 2 to the power of 3. If I do pow of 2 comma 2, then that should yield 2 to the power of 2, then 2 to the power of 3, and 2 to the power of 4. So the first thing that I'm yielding is always n to the power of p. I'm going to yield from some iterable, and that iterable is actually the iterable given back by this generator object. So we can recursively call this generator object, and let's try to figure out what the parameters might be. So we still want to yield the powers of n, so n has to remain the same. But in the beginning, we said, okay, yield 2 to the power of 1 when the input was 2 comma 1. Next, we actually want to yield 2 to the power of 2. So now I want to yield from pow of n comma 2. And the time after that, I want to yield from pow of n comma 3. And the way I can do that is just every time I can increment p. So next time I'd yield from pow of 2 comma 2. That would yield 2 squared. And then after that, like the bookmark would go further, and it would yield from pow of 2 comma 3. So that would give me 2 cubed. The other part of this problem is figuring out like how I actually yield a bunch of these generator objects. And for that, I can just use my while loop here. And since we can yield an infinite number of generator objects, our while loop condition can just be while true. So that would go forever. And since we want to yield a generator object, we can call this pow function, since this pow function gives back a generator object. We can just call this pow function with n comma 1. The way I got that was I'm using n to keep track of like which numbers powers I'm yielding. And p starts at 1 because I first want to yield to the first power and then to the second power and so on. So that means I also have to increment n. So I'll start with n equals 1, yield this generator object. So that would be p1, and then increment n, and that would be p2. Increment again, and then it would yield p3. p1, you can see, would be like a bookmark in this function, and n here would be 1 and p would be 1. So the first thing it would yield would be n to the power of p, which is 1. Similarly, if we called next on p2, it would yield 2 to the power of 1 because that's our second generator. That's how we made it. That's pretty much it. Does anyone have questions? the second yield is what we yield from the main function. Yeah, so this one is what we're yielding from the main function. And it yields a generator that we iterate through. Exactly. So the way we iterate through that generator is by repeatedly calling next on it. So this is us calling next on the first generator and the second generator and the third generator object. And yeah, exactly. P1 and P2 and P3 are all generators, which were given by our main function. Why is it that we don't need a while true in the first generator? In the first generator, we're not iterating, and the while true is kind of implicit because we basically yield some value, like 2 to the power of 1, for example, and then we yield from like another generator object with like the arguments 2, 2. That will just yield 2 to the power of 2, and it'll yield from a generator with the arguments 2 and 3. That will yield 2 cubed, and you can see that this will keep going on. So the reason is because we're doing this recursively and we don't have some sort of base case. This will keep going forever. And that's not a problem because this is a generator and we have lazy evaluation as opposed to like trying to compute everything and running into an error.
We could have tried to define POW in a different way, such that we used a while true statement and it would iterate continuously. But that would require like a slightly different skeleton. But it is possible to use a while true statement within POW instead.
Yeah, I feel like we could just do something like while true, yield n to the power of p, and then increment p every time in this loop.
Mm-hmm. And you can see that it's a very similar idea here. We're just incrementing p every time, and we're yielding that answer. Any other questions? Which technique are you referring to?
I'm saying like we can use either recursion or like a while loop of infinite while loop to do the same thing for both generators, right?
Yeah. The only problem being that we can't do that because the skeleton is kind of restrictive. And if we wanted to use recursion for the other generator, then we'd actually need some sort of parameter in POW naturals because there's this variable n that we're keeping track of, right? So if we had some variable n, then we'd yield this and then yield from POW naturals of n plus 1.
Oh, okay. Okay, thank you.
All right, let's do another problem. And this is the answer key. Let's just make sure it matches. All right, looks good to me. All right, so this is infinite generator, which is going to take in a list and yield each element of that list. What it's going to do after it's done yielding every element of the list is it's going to cycle back to the front of that list and keep going. So for example, if you call infinite generator on this list 1, 2, 3, you'd yield 1, 2, 3, and then back to 1, 2, 3. And there's a hint here. You don't have to use it, but you might find it helpful.
Yeah, also, same thing as before. So if you finish this problem, feel free to PM us or message the chat that you're done. Or if you're confused, also feel free to PM us.
Could you let us know in the chat if you are stuck or done? And if anyone has ideas, then feel free to shout them out as well. Could you briefly explain why you chose to use an iterator here?
Yes, because a list is not an iterator, it's an iterable, so we have to convert it to an iterator before we use next on it.
Okay, but do we have to use next on it?
No, we probably can use yield on it as well.
Yeah, so we can yield the elements from the list, and that will create a generator object or an iterator for us that then people can call next on here. So we actually don't need to create an iterator from it. And we might run into some trouble like before where we had to do like a try catch around the next.
What catch are you talking about?
When we run out of elements in the
Oh,
iterator, then we get the stop iteration error. And so it might be easier to just keep track of some index and then yield elements at that index. So maybe like instead of having the iterator, I could just say like I equals 0, which is the same thing, like it's similar. But then we could just yield the element at like the first element of the list, and then yield the next element of the list, and so on. Oh, okay, my bad. I didn't know it was cutting. But what I was saying was that we can just have like an index I equals 0, yield the value at that index, and then yield the value at the next index, and so on. So let's try to see where we can go with that approach. So what should I yield in here? Also set a list of, I hope that's an I, and then, okay, so did Zoe. Okay, great. Yeah, so it is list of I. The first thing that we yield is in fact list of 0, but then after that we might want to yield like list of 1 and so on. So we can do list of I. So that's right. And that will mean that the next iteration of the loop we yield 2 and then 3. But then after that we'd run into some problems because when I is equal to 3, then that's out of bounds. So we need to come up with some more clever way of incrementing I here.
Could you use mod?
Yep, how should I try to use mod?
So mod by the number of elements in the list.
Sure, let's do that. So I is equal to I plus 1, but then mod that by the result, by the number of elements in the list. So what that is, and 1 mod 3 is just 1, 2 mod 3 is just 2, because they're all less than 3. But then after that, in order to cycle back around, usually if I incremented this by 1, I'd get 3. But when I'm modding it by 3, then 3 mod 3 is just 0, and that allows me to cycle back. And then I can continue forever. So lastly, what should the condition of my while loop be? Yeah, we want to do this forever. So that works. Any questions about this solution? All right. Tim also mentioned an alternate solution where instead of using like indices, we could say like while true, so forever, yield all the elements in list, yield from list. And once again, this is equivalent to like while true for val in list, yield val. And what this would do is it would yield all the elements, so 1, 2, 3, and then it would iterate again, yield all the elements again, 1, 2, 3, and so on. Any questions about this other solution?
Yeah, can we yield from list before making it an iterator? Because we haven't done. Or does it? Yeah, could you explain why we could just yield from list?
Yeah. So if you, okay, I'm just gonna go ahead then. So if
Okay.
you look back at the idea here of yield from, which is just like syntactic shape, right? So Akshat wrote out this idea of like for val in list. So if you remember before from what like a for loop really does, a for loop is just like a while loop, except we catch that stop iteration exception. So implicitly, that for loop will make an iterator out of this iterable and get all the elements. So this will work because we can iterate over an iterable using a for loop.
Yep. So yield from works for any iterable, and iterators are just a special class of iterable. So it works for those as well. Cool. Any other questions about this?
So the second solution just means that we won't be using all the lines, right?
Yeah, that's what that means.
Okay.
We are out of these problems. We can certainly do another problem if Tim has found one. Tim, have you found
Yeah,
one?
were you interested in the partitions generator?
It might be too long. What do you think?
Okay. In which case, I think it's okay to do the Spring 15 file. I'll share my screen. This is a shorter one. So.
Cool. You can do that.
Yeah, is the screen being shared correctly here?
I see the spreadsheet, but earlier I saw the slides.
Oh, unfortunate. Let me go ahead and stop sharing. Okay, yeah, that should be better, right? Anyways, yeah, so here's the question. Yeah, so this is called amplify. So the idea of amplify is that you will be given some iterable object and some function, and you will apply the function and you will yield the result of each application of the function again and again until it's no longer true. Sorry, actually, I might have misspoken here. You're just going to be given some object x or some like value x, and you're going to apply the function to that value x multiple times until it's false, in which case you will no longer yield values. Yeah, so you'll have some more time to do this one, like maybe like 5 minutes or a bit less. If you're done, same thing as before, just message one of us or say in the chat or tell us. And then we can go over it. Yeah, once again, if you have any questions, feel free to ask. And also, if you're done, also feel free to tell us that. Okay, I think it's been around long enough, 6:24, and we can get into some discussion here. So does anyone want to talk about a solution they're able to reach, or like their general thinking process? If you want, you can put in the chat, or you can also just talk about your solution. Okay, if not, then I still talk about in general this problem and what it's asking you to do. So currently, based off the problem, it tells us to get the particular yield elements with this particular function applied to some particular element. So for example, yield the longest sequence x, f of x, f of x, and so on and so forth, that are all true values. So keep in mind that we could have, let's say, had a true value, or that could always be a true value. You could have something that was always a true value. So it may not actually terminate. And that's the way I have this while statement over here. So for example, for something that would not terminate, like if we were to call amplify on lambda of x at x minus 1, comma, like -1, then this will always be true because we never go past 0 this way. And so you have to sort of keep that in mind, that we are going to potentially yield some infinite sequence here. Okay. So we do have some sort of stopping condition though, which is a case of, is our particular value false here? So based off that, like, what do you think we should give as our conditional statement or our while statement here? Like, what should we be checking for? And you can put this in the chat or talk about it if you want. A while x and while f of x. So we actually have two different things here. Use mod to fx. Okay, so fx, f of x and x. Okay, so you have some different answers here, x and f of x. So does someone who has x or f of x want to explain their reasoning?
Yeah, I think x is the previous value, and then f, by applying fx, we'll be able to test out if the next value is false.
Mm-hmm. Yeah. So the answer here is actually going to be x. It is actually going to be while x. So if you look at this particular example at the beginning here, it says yield the longest sequence x, f of x, f of x. So we only want to yield some particular value, assuming that the value itself is true. And additionally, yeah, so when the next value to yield is a false value. So for example, if we found, let's say we said that like f of x. So for example, we evaluate f of x, we would still want to yield x though. So maybe our starting example is like, we started from 1 instead. So if you go back to this idea of like lambda x, so amplify of lambda x and x minus 1, comma 1. So we still want to yield 1, but we don't want to yield 0 because that's a falsy value, right? So if we first do like f of x, we'll be looking at while 0, and that's false, right? So we're never going to be able to actually yield x. So building off of that idea, this is why we need to do while x instead of f of x. And here we're going to be yielding x based off that same idea that first we check, is this value true with this while statement? And then if it is true, so we'll move on to the body of this while statement, we'll yield this particular value. Does anyone want to talk about what they think the final line should be? So yeah, this final line here. Yield from amplify f of x. Okay. Okay. That's an interesting idea. Yes, that will work. Yeah, that will work. But so amplify of f comma f of x. I will say it's a little bit extraneous, perhaps. So sorry, I didn't actually write that correctly. That will work. So this doing recursively will work. yield from amplify of f of x. Actually, sorry. Actually, not quite. Actually, sorry. This is it's not a bad idea. They're a recursive idea, but the issue is that we already have this while statement here. So let's say, for example, our first value is true, and amplify actually works. So then this would yield x, and then it would yield all of the remaining values in the list. But then it would yield it again because x is still true, and continuously again and again and again. So you notice that because we never update x, this statement is always true. So that wouldn't quite work. It's a good idea though, and we could, yeah. So we have here x is equal to f of x. That is the answer. I'll talk a little bit more briefly about amplify f of x. So that would get close to working. It's just that we would have to take out the while case essentially. So we'd have to have an if statement instead. But then we could use a similar structure with like yielding from amplify f of x because like we're storing essentially our f of x value. Anyways, so yes, it is going to be x is equal to f of x. And the idea is here is that we're just updating our value x. So if our value is true here, so it's true, x is true, we're going to yield it. And then we're going to update it to be the next value in the series. And eventually we'll stop because f of x will be false, or maybe we'll never stop because maybe the sequence never ends. Okay, right now it's 6:30, so this topical review session is over. If you still have additional questions, feel free to ask. But for now, we are done. Everyone's here. Good luck on the final. And I would also very much encourage you to take the practice final that was occurring right now. But take it if you have the time at some point later on. It's very helpful. It helps you learn the material much better, I think.
Yeah, we've released the questions. So even though like a couple of questions aren't working for Windows users, you should just be able to like download all of them unencrypted on Piazza now. Great. All right, thanks everyone for coming. I'll stop the recording now. If someone has more questions, we are happy.